Introduction. Copernicus Technologies.
Copernicus Technologies is a company that develops and sells intellectual property, ideas. And we have an idea that we feel is very important, and we'd like you to know about it. It's called the synchronous time base, and this executive summary will provide an overview.
Essentially, the synchronous time base is a way to make the internet go faster. But it is also much more, as we'll see.
The internet is currently approaching a state of crisis. Demand for services and speed is growing much faster than the capacity to deliver those services. How to meet that demand has become one of the central issues of the day, both politically and economically. But to understand the problem, we must first understand what the internet is and how it came to be.
Part 1. The Internet.
Originally, the internet was never intended to be the multimedia extravaganza that it is today.
In the beginning, it was little more than a text messaging system, used first by the military for command and control functions, and later by professors at universities to exchange research and ideas.
Since it was basically an electronic mail system, it was modeled after the real mail system.
When you drop a letter off at the post office, there is no overriding intelligence that plans the path of your letter. The workers in the local office have no way of knowing exactly what path your letter will take on its way to its destination. They simply look at the first few digits of the zip code and put it on a truck that is going in the right direction. Further on down the line, the letter is sorted again, put on a different truck, and the process is repeated. At each junction, the sorting grows more specific. First the state, then the county, then the city code, and finally the neighborhood. At last, the letter is put in the hands of the person who actually delivers the mail, and that person knows where everyone on their route lives.
This system has certain advantages. First, it is resilient. If the mail can't go through by one route for some reason, say because a bridge is out, then the system automatically routes the mail around the obstacle. It just puts it on a different truck that is going in a similar direction. Second, this method uses a minimum of administrative overhead. The postmaster in your town doesn't need to sit down and figure out exactly what route your letter will take, and then call everybody in the system to inform them of the plan. Instead, each letter is autonomous, in that it has an address printed on it that will guide it through the system.
The Internet is like the mail system. We call it a packet-switched network. This means that information, like this video, for example, is broken up into small pieces called packets, and each one is individually stamped with its destination. The packets are then tossed into the system and bounced around from junction to junction, being sorted as they go, until they get where they are going.
It's easy to see why the internet was first designed this way. In the early days of networked computer systems, things were fairly unstable. Every computer had its own unique operating system. There were very few standards of any kind. You never knew when someone's computer or their connection might go down. And processing power and memory were very expensive and hard to come by. They needed a system that would work as reliably as possible, while remaining as invisible as possible.
But the creators of the Internet could have hardly imagined that the humble messaging system they were building would go on to spark an information revolution, redefining commerce, communications, education, and entertainment.
And it turns out that while the basic design of the internet has served us well to get this far, it is now clear that to go much farther, some things will have to change.
Part 2. The Traffic Problem.
To better understand the challenges that the internet faces, we need to take our analogy a little further. If the internet is like the mail system in the real world depends on roads to move the mail from place to place. And what is the primary obstacle to moving things around on roads? Traffic.
Like your town, the Internet has many intersections. At each intersection, packets of data are captured and held briefly while other data moves through the intersection. This is very like what happens when cars are stopped at a stoplight. Periodically, the light will change to allow traffic to flow in different directions while other cars have to stop and wait. The more cars trying to move through the intersection, the longer the wait becomes.
As any commuter knows, the amount of time it will take to go from one end of town to the other depends greatly on how many lights are between you and your destination and on how much traffic is present at each of those intersections.
In the virtual world of the Internet, this stop-and-go process is called buffering, and it causes delays in the movement of information.
But the analogy doesn't end there. A savvy commuter also knows that there are many different paths to reach the same destination. Depending on the time of day, you might take the bypass, or the frontage roads, or Main Street if it's 3 o'clock in the morning.
Similarly, in a computer network like the Internet, there are many different paths that data can take to reach the same destination. But in a computer network, all these choices can actually create more problems, as we'll see.
Part 3. Breaking it down.
If we're going to help the Internet go faster, it's time to get really specific about what it is that makes it not fast.
First, there is the delay that happens at every junction while packets of information are sorted and buffered before being forwarded to the next junction.
The more junctions, or nodes, that packets must pass through, the longer it takes for information to reach its destination. This is similar to the traffic lights and intersections of a city.
Next is the problem of randomness. A packet of information traveling on the Internet does not have the ability to make decisions about the path it will take, the way that a driver in a car can. Instead, each packet is directed automatically by its address.
Like a letter in the postal system, packets are simply bounced around from junction to junction until they eventually arrive at their destination. In fact, there's no way to predict or even trace the path that an individual packet might take.
For this reason, the Internet is often depicted in diagrams as a cloud, representing the uncertainty of exactly how the packets are passed along. The biggest disadvantage of this is that the data may make many more hops than it needs to. This introduces another problem, that of addressing. Inside the Internet, addresses have little correlation to physical locations. Addresses that are similar in the virtual world might be located on opposite sides of the country, or even farther.
When these two problems are combined, that of randomness in path planning and addresses that are not correlated to the real world, an even stranger problem is created. Packets sent sequentially will often arrive out of order.
For example, if we were to transmit this video over the Internet, we would first break it up into little pieces and address each one. We would then throw them into the cloud of the Internet, and they would have to find their way. Some might go through Detroit, others might go through Pittsburgh. Still others may travel to Hong Kong or London before arriving at their destination. Because the paths are all different, they arrive at different times, out of order from the way that they were originally sent. This is why, whenever you watch a video from the Internet, there is a scrolling bar at the bottom of the window that says, buffering. Your computer has to wait until it has enough pieces to start putting them back together in the right order.
If the pieces don't arrive in time, the video playback will stutter, or stop, while your computer tries to get things back in order again.
Finally, all the problems we've described get worse according to how much traffic is happening in the system.
All in all, there are a lot of barriers that make it difficult to do things like real-time audio and video, two-way communications, or any one of hundreds of other applications that require the fast movement of information in real time. If the Internet is to reach its full potential, it will have to address these problems.
Part 4. The Copernicus Solution.
From a marketing standpoint, a successful idea should either solve a problem or fill a need. And the most successful ideas are those that can do both, while eventually creating whole new markets.
The Copernicus solution is just such an idea. In fact, some might call it a platform technology because of the large number of problems it solves and the wide potential for marketable applications. Put simply, the Copernicus solution is a way to synchronize the movement of information. We call it the synchronous time base, and it can be applied in different ways to make all kinds of things move faster and more efficiently. For now, let's focus on how the Internet can benefit from a synchronous time base. Let's return to our traffic analogy. What would happen if every driver in your town were a highly trained professional stunt driver? What if we gave each of those stunt drivers a big clock on their dashboard and then synchronized all the clocks in all the cars?
Well, in addition to cutting down on road rage, we could create a coordinated timetable that each driver could refer to. Any given driver could know, for example, that they need to cross a given intersection at exactly 3:45 and 50 seconds. If the driver goes through early, say 3:45 and 49 seconds, the driver will hit another car. If the driver goes through late, at 3:45 and 51 seconds, they will be hit by another car. But if they go through at exactly 3:45 and 50 seconds, the car will breeze through the intersection without having to hesitate. If all the drivers were good enough, everyone could drive straight through town at high speeds and never have to stop at all.
We would call that a synchronized driving environment. Traffic could speed up to the very limit of what the cars and the road can handle, and capacity for moving things would be greatly increased. Of course, in order for such a scheme to work, there are a few things that have to happen.
It would be very important that the dashboard clocks be accurate and synchronized with all the other dashboard clocks. It would also be necessary to know exactly where every intersection is and how far apart they are. Finally, the timetable would have to be agreed upon by all.
In the computer world, data moves very fast. In order to synchronize data, you would need a very accurate clock.
The most accurate clocks so far created are atomic clocks, but they are very expensive, cumbersome, and difficult to maintain.
It is unlikely that anyone would want to stick an atomic clock inside their desktop computer or handheld device, but they don't have to. That's where Copernicus's patented technology comes in.
It turns out that there are lots of atomic clocks readily available to anyone, anywhere. The GPS satellite system uses the timing data from atomic clocks to triangulate position. Every GPS satellite has 4 atomic clocks on board. At any given time, you might be able to see 4 to 8 satellites in the sky. Each clock on every satellite is constantly checked and cross-referenced with a set of 10 atomic clocks on the ground. So, at any given moment, you can access the averaged sum of up to 42 atomic clocks, all consistently monitored to be exactly in sync with the universal time standard.
And all you need to take advantage of it is a small antenna. It's available anywhere on the planet, 24 hours a day, and it's free.
Using GPS as a clock for computer communications has another advantage. Besides telling you exactly what time it is according to a universal standard, it will also tell you where you are in relationship to everything else.
So in one step, we've satisfied 2 of the essential components of our synchronized traffic system, that of an extremely accurate clock and an accurate physical location. All that's left is to decide on the course that our information will take, and a timetable for scheduling that course.
Part 5. Path Planning and a Synchronized Internet.
Any protocol for sharing data between computers isn't much good if the protocol itself is too complicated. You end up spending all your time transferring information about your protocol instead of sending the information that you actually want to use.
So the Copernicus solution uses a minimum of overhead, in keeping with the same principles that the original designers of the Internet came up with for their mail system. Each junction, or node, of the network only needs to know where it is, what time it is, and what that one node is immediately connected to. It then becomes possible to do very efficient path planning.
By attaching a geographical location and a time index to the address of every packet, nodes can use vectors, a very simple mathematical tool, to route the data effectively.
Also, because there is now a common time index for the entire system, we can pull off the trick of moving data through intersections without colliding using a concept called time division multiplexing, or TDM. In time division multiplexing, you take a unit of time, say 1 second, and divide it into small pieces. You then designate certain pieces to be used for certain things. You could divide it by direction. Information going one way uses a certain part of the second, and information going another way travels during the next segment. Or you might make the first part of the second for video information, the next part for audio, the next part for text. It's almost like different channels on cable TV, only you change channels by changing the time period you use to tune in to the internet.
There are several ways to use TDM, but the result is that information can move freely on the internet without collision or buffering. But the really big news is what happens once these two ideas, path planning and TDM channelization, are combined. Let's look at our list of problems again.
Delay. If we can coordinate the information traveling through intersections, we can reduce the time it takes to sort and buffer information. Delays are greatly reduced, and everything moves faster. Randomness. Through efficient path planning, we can find the most consistent and direct route for sending data. This increases speed while decreasing the total amount of traffic on the internet at any given time. Addressing. By attaching a real-world location to the address on a data packet, it can travel directly through to its destination without being bounced all around the system. This reduces the total number of intersections that the packet has to go through. Order. By using all of the techniques above, data arrives sequentially in the same order it was transmitted. No reassembly required. Traffic. By moving data faster and more efficiently, all data spends less time in the system. This translates into a substantial reduction in traffic, while enabling the same amount of information to be transferred.
A reduction in traffic also means that there is more available bandwidth on the internet at any given time.
Part 6. Implementation. The WiMAX window.
So all this sounds really good. Without having to change the infrastructure of the internet at all, we can change the way we use the internet to get lots more mileage out of what is already there, or from whatever is yet to come. But it does no good unless there is a way to implement the idea. The problem with new ideas in the internet is that there is no one governing organization that decides what the standards will be. Standards are proposed, discussed, and gradually adopted over time. Historically, the bottleneck has always been that a new standard is only useful if everyone does it, but no one wants to do it until everyone is. The resulting stalemate means that new ideas take years to implement. To overcome this, the Copernicus solution is scalable.
That means that it can be implemented a little at a time and generate real advantages wherever it is deployed.
But right now, there is a much greater opportunity for the growth of a new standard.
You've probably heard of WiMAX. It's a new wireless internet standard that the whole world is talking about. It has many advantages over both wired and existing wireless internet delivery systems. Because of these advantages, many countries in the world that currently have little or no internet access for their people are looking at WiMAX to be their internet system. Huge populations in Asia, South America, Africa, and India will soon be receiving internet access through WiMAX technology.
So here's the big deal. You only get one chance to build an internet for the first time. In the United States and Europe, that chance came and went decades ago. Once a system is built, it becomes much more difficult to modify. but these developing countries are starting from scratch. So the window of opportunity to deploy a better, faster internet is wide open right now. The Copernicus solution is the perfect partner for these developing infrastructures. In fact, the leading WiMAX implementation already uses GPS timing to synchronize its data. This is an ideal foundation for deploying the synchronous time base. Later, the backwards compatible synchronization protocol can migrate through the rest of the existing internet. There could be no better time for the internet to take the next logical step in its evolution. The synchronous time base is that next step.
Conclusion.
We at Copernicus Technologies are very excited about the potential of our intellectual property. We are currently seeking a small amount of capital to mobilize our technology and reserve our market presence. If you are interested in participating in the next generation of information technology, we invite your inquiries. We would be happy to personally respond to any questions you may have. This concludes our executive summary.